Hello guys, we're gonna start now. So this is efficient CAD. The name itself is pretty efficient, it's like just efficient CAD. And my name is Rachel Kim, and my name is Elin Kim. And we'll start the presentation. To introduce us, we're the co-director of design and director of electronics for 694, and we're also on team FTC 23. So this is like a very brief summary because we have a pretty long presentation about what this is going to be about. So I know you can have like amazing bug without having like the best CAD, but you can also have a not so amazing bug with a very good CAD. But what makes like having an organized CAD is good to have an organized CAD is because it's easy to work with multiple people. Like it's not only one person design the entire robot, you'll at least have 5 people working together. So it's easier if you have an organized CAD, then everyone can work together easily. And also it makes iterations more easy. Let's say you want to make this quick change, like even a quick small like dimension change. It's nice to have if you have a CAD that's very organized because you just change one number and a lot of things will adjust with it. And it's also nice to make complex parts, like stuff that require like complex like shapes, which we'll kind of get into like the examples. And it's also very less stressful because it's very like beautiful to look at when you see your complete CAD and if it's very organized. So these will just be this presentation is based on the fact that I hope many of you guys know how to already use a little bit of Onshape and the Onshape basics. And this will be kind of it won't be on like the basics of Onshape, but it's kind of going to be on like how to make your CAD like life easier, and it's like more of like tips and tricks based on that, but it's based on the assumption that you guys already know how to use a little bit of Onshape. So over the past few years, these are some of the things we've added, and if you see, they're like pretty like decently complex, but throughout the years, we figured out like slowly through each like mechanisms and stuff like that, we figured out what the most ideal way would be to CAD, so that when you make iterations and when you make changes on the CAD, that will be so much easier. So these are some of the things we've learned throughout like making these projects. So this is just a few examples. Okay. So we'll start off with the robot master sketch. So this will be the first topic of the presentation. So basically a robot master sketch, this is just one example of it, is basically you have it basically sketches out all the basic parts on your robot, like mechanisms, through sketches. So there's nothing 3-dimensional here. This is all just purely 2-dimensional sketches that are offsetted using different planes. And the reason why we started this during this season, the 2025 season, is because we first saw it through a team mechanical advantage. And we thought this was very highly efficient and very useful for the entire team, not only for design. So for example, for the design department, obviously it helps mech leads understand the relationship between mechanisms. So like for instance, you're not going to only have a drivetrain on your robot. You have like different, like especially in 2025, you have like elevators, you have like end effectors on it. And it basically helps mech leads understand the relationship between the different mechanisms. And it also gives like members outside of design a better understanding of how your robot will look like, even before the whole thing is fully 3D modeled. So for instance, software can basically understand how the robot will function. Like for our design, it had like an elevator with a pivoting arm with an end effector. So it basically gives software an understanding of how it looks like, so they can have something to work with even before the design is finished. And same for like any other members, like maybe like business members, they can have a lot more better understanding of it. And then this is just one of the examples. Kind of hard to see because it's just a lot of different sketches. So I'm going to go into more specifics. And also this presentation is going to be a mix of both FRC and FTC, but both the lessons, what are the examples, FRC or FTC, they can apply to either competitions and different like robots. So on a robot master sketch, basically there will be a lot of things included, and it also highly depends on whether it's in like what type of game it is. Like if it's a shooting game, you'll have like a shooter. If you have like a pick and place, you might have like an elevator or like a double door jump. So it really depends on the game. So I'm not going to go into specific of how to master sketch like an elevator, but I'm just going to give a few examples and like key components that do include in a robot master sketch. So obviously the first thing that you always include for FRC and FTC is a drivetrain, and which is why that's the only thing that's basically labeled, because the rest totally depends on the game. And yeah, so like mentioned, it depends on like the type of mechanisms you have. So moving on. And so on the robot master sketch, there's a lot of key parts that are very important, because otherwise it might further mess up with your progress if you make mistakes on it. So it obviously, the relationship between the different mechanisms. So like on your robot, you have a lot of different mechanisms. You're not gonna only have like a drivetrain with an elevator. You also have like end effectors on it, and defining the relationship of how they go and work together is what is basically represented on the master sketch. And you also have field elements, because your whole robot depends, your whole robot dimensions and everything will depend on the field elements. And obviously the game piece, like if you have an intake, you're intaking the ball, you would like kind of draw out the balls for it, or like the game piece. And sometimes some electronics does help. We sometimes do, we sometimes don't do it, because in FRC, like usually batteries do take up a lot of space, and maybe marking the location under master sketch does help with the electronics members and also the mech leads. And how the robot master sketch works is that there's nothing three-dimensional. There's no extrudes. There's like it's basically formed out of sketches and planes. So like mentioned, your different planes and sketches from different perspectives. So you have stuff from the top view, you have some from the side view, you have some planes that are offsetted, and it overall creates a three-dimensional effect, which you can see from the example here. And they're within the Onshape part studio for the master sketch, they're divided within folders to create like for the different mechanisms. So like some of them are like the main sketches, some of them are divided between the different mechanisms. And and this is just one example for the FTC robot for this year. So like mentioned in the previous slide, field elements are really important. So this is for our 2025 robot for OnVary. Here are the field elements, for instance. It doesn't have to be really specific. The field elements can be very simple. Like the bars, you just show how like wide it is and how tall it is. And this is a very, very simplified, just literally show the all the 4 levels without being too specific. And here on both sides, you can see the HP station to show how the type of angle the coral will be dropped at, so we can know like how high the funnel needs to be, or like what angle the funnel needs to be. So the robot master sketch not only includes the robot itself, but also includes the field elements, is the summary. So if you notice that the elevator is here, and this is where the coral will be on the end effector, so you know like approximately what angle your arm has to be to score on each of these levels. Yeah, and to make sure that all levels are possible for like with the constraints you have. Okay, so in order to create this three-dimensional effect, you need to use a lot of planes. And planes, I feel like, are things that are kind of very, very underrated in Onshape, because there's so many different ways to create planes. There's a lot of options to create the planes. So some can be like parallel to the right plane, some can be parallel to the top plane. Some can be even angled. So if you see here, there's like angled planes that are not really like this one of the standard planes. And because through the use of a lot of like planes, it creates a 3D effect while only using 2D drawings. Which is kind of very, very nice, since you don't have to extrude anything in order to represent how the robot will look like. With just simply sketches, it looks like a robot because of the locations of the planes and the sketches in the three-dimensional space. So the highlighted ones are just the planes. So this is an example. And I think this was mentioned before, like in the previous slide, it was just like a photo of it. But the entire master sketch is in one part studio. In the main document, because since they're only sketches, so they're not going to take up a like lot of loading time, so it's okay to be in all one part studio. And they're divided into also, this is an FRC example, so you have like the field elements like I mentioned before, and the different mechanisms. So I'll just show you a quick example. It's not going to go in specifically on like how the robot works, but it's just going to show you how like it gives a three-dimensional effect. Wait, just connect to that. Because like I mentioned before, it really depends on the type of game it is. So just. So for example, so like for example here, there's a lot of aspects to like, and the reason why I'm showing an FTC example, I would love to show an FRC example, but this was the latest one. And every time you like CAD a new robot, I guess you make improvements to it. So the FRC example that I have is the one that's for On Mary, which is kind of like outdated since it was like almost a year ago, which is why I'm showing an FTC example. So for example here, there's like multiple sketches to it. So this is the side view for all the main parts to it. So basically it's a shooting game. You have an intake and you have exit through the shooter. So these map out like the ball path of where the ball will go. So when you guys are mass sketching and when you guys are kind of like confused on where to start, think about what viewpoint is the most important. So originally we started with the top view of the drivetrain, like the top view this way. But then we realized everything is usually dependent on the side view because the side view shows how the ball travels. But the side view shows like the ball traveling path and everything that's important, and even the like the drivetrain belly plate height, like this represents the belly plate here, and where the shooter flywheel will be. So we realized that the side view is the thing that determines everything, which is why we changed by starting with the side view and then moving on to the top view. So then we link everything that corresponds on the top view. So everything that everything that links with the top, everything on the top view here is linked with the side view, so corresponding parts, like the rollers, I guess the belly plate, everything that's related are linked to each other. So you gotta think about what viewpoint you want to start at. And also, yeah, applies to FRC. It's slightly different for FRC because you'll most likely start with like a drivetrain. So yeah, that's just an example. And like mentioned before, we're not going to go into too specifics because it really depends on what type of mechanism you have. Also, if you guys have any questions, you guys can like raise your hand in the middle of the presentation. Oh, yeah?
What exactly iteration do you do? Like, when you just get it, do you start master sketching or what?
Yeah, so it's when after like prototyping season is like over, like you start to know which prototypes you want to put on the robot. So after we flesh out like what kind of mechanisms we know is going to be on the robot, we then start like master sketching. And even like even during prototyping, you also need to like do something similar where you use the field elements to see the relationship between the mechanisms. Like if I'm like, let's say prototyping intake, that even if I'm not sure it's going to be on the robot, I'll do something similar where I find a relationship between the field elements and like let's say the roller of the intake to do that. But usually we'll start this after we like know what mechanisms will be. But also like sorry, like even if before like what you mentioned before while prototyping, you might want to see different like robot archetypes. So we didn't first settle on we didn't immediately start the season and be like, oh, we want like a elevator with a pivoting arm with an end effector. That wasn't that immediate conclusion like many teams. We wanted to try different archetypes. We didn't want to do the donut climb. We wanted to do like different types of climbs, but we don't know if that will fit within like one single robot. So robot master sketching might not only be for your like main robot that you're actually building. You could kind of use a lot of like small sketches at the three-dimensional to make a three-dimensional effect to see different type of archetypes. So our last arc, the design kind of did that to see whether we want like a static shooter, maybe we want a pivoting arm. He kind of arranged the sketches to see what type of archetype you want to settle on, and that also kind of helped us settle on. And also through master sketching, our shooter on Mary, it wasn't supposed to be doing algae, like shooting into the barge. But while master sketching, we realized it kind of reaches, like if we swing it a little bit, it reaches, which is why we added that algae mechanism. So it's kind of like master sketching helps you. It's like good for visualization, and yeah.
How many members typically work on a master sketch?
I think it does depend. Since we start like last year, so it's like kind of hard. Like last year, I would say like 6. Yeah, it's like one person. Like each mech lead, I guess, would start master sketching on the like I guess the main part studio after like one person has set the drivetrain. Like after one person set the drivetrain, then all the rest of the mech leads come and add their mechanisms onto the. Like starting from the drivetrain. And that's why it's also kind of important to know which mechanism needs to, because you know how like Onshape part studios work. When you create the first sketch, the second sketch is after the first sketch. So the first sketch cannot be dependent on the second one. So the order in which you create the sketches do matter. So for example, before the arm, you would make the elevator so you know how high the elevator goes. Or like you might have a very simple sketch with all of them combined, but like the order in which you create the sketches do matter, and that kind of involves a lot of like thinking and discussion between mechanism leads. So another very, very simple example, since this will be universal for all like FRC teams, is a drivetrain. So the reason why I'm showing a drivetrain, the reason why I'm showing a drivetrain is because that's, like I said, universal. So I'm just gonna suppress do the robot bar to hide everything except for the drivetrain. So here's an example of a drivetrain. The reason why I think the drivetrain is like one of the most, like obviously the most, it's very important, but one of the most important part on a master sketch is because you have a lot of things that are gonna go on your drivetrain. You're gonna mount majority of the stuff are gonna interact at least like part with the drivetrain because it's being mounted onto there or in some other like matter. And if something like one small thing, like let's say a whole like inch is off with, or like half an inch is off for like the holes, everything won't line up, which is why it's very, very important to have a very accurate drivetrain sketch, which is why I'm showing this as an example. So for instance, this is only the drivetrain part of it. So if you see here, it's very three-dimensional, like I mentioned before. You could kind of make out the shape and like size of the tubing based on pure just sketches of this bottom view. So it's going to be mentioned in the slide later, but if you see here, the drivetrain tubing is not right directly at the origin, and it's floating above, and this is because obviously you have the sewer modules, so your tubings won't be directly on the origin. So we also we're very conscious about like where we place our sketches and where we started.
So basically, the origin represents the ground.
Yeah. So you don't want the tubings to be like directly touching the origin because that's not the ground. And also this makes it easier because let's say someone's master sketching an intake, and if the drivetrain the origin represents the ground, everyone can universally say.
Yeah, I was just gonna ask: is there an advantage to sketching out the drivetrain rather than building your master sketch off of a 3D assembled drivetrain?
Yeah,
that's the one thing that stays stagnant, right? You're gonna design all.
Oh yeah, that's true. The reason why we do sketch instead of assemblies, because let's say you need to change your robot dimension, and this was something that actually happened during the season. We weren't sure if we want like a rectangular robot or a robot that leans more towards a square. So that's why we were like trying to adjust the dimensions, and which is why it was a lot easier for us to do in Sketch. So let's say we realized I want the drivetrain to be like 29 inches like in length. Let's just change it, and it's a lot easier to change with Sketch because if you just see right a second ago, this is 28 inches, and then we could just easily change to 29 inches. So like it was a lot easier to change the dimensions through sketches rather than assemblies when we need to make quick changes, which is why it also really helped us. We have a lot of things on our 2025 robot. It was like it literally looks like a factory because we have so many different types of mechanisms on it. And in order to figure out the exact dimension of the drivetrain we need to be able to quickly adjust the drivetrain size. And basically we just kept adjusting until it seems like everything seems to fit. So for example, like here, when I adjusted the whole set, the dimension of the drivetrain, the number of holes in the tubings all adjust with it, which is why it kind of did help a lot because it was this whole sketch and master sketch is pretty adjustable. And even if the origin represents like the ground level, it should also be the center of the robot. Because this came in use many times. Like for example, at the end, after you like done CADing everything, and the software needs to know what angle and where is the limelight or vision located, and they usually do it based on the center of the robot. So when we give them like distance between the lens and like the center of the robot, you can just click on the origin and then the lens, so it makes everything really easier. So you don't have to calculate everything. Yeah. And like I think I was talking about before, like if you're master sketching intake and you know that the origin is always the ground, it's a lot easier. You don't have to ask the person who designed the drivetrain. Is this the ground or whatever is the ground? Like it's like everything is unified, which is a lot easier. So yeah, this is basically all what I mentioned it before. And the last thing about probably not the last thing. The most important part about the robot master sketch is what I mentioned, the relationship between mechanisms. So I'm not going to go into CAD, it's going to take forever to load. So, and this is just one example. So basically how a robot works is there's a coil that enters through the funnel, and then it goes straight into the shooter, and then the arm moves up to score. So if you see here, this part is the shooter, and this part is the funnel where the coil enters. And some parts are hidden for better view. So the relationship between the funnel and the shooter is that the exit point of the funnel has to align with the entering region of the shooter. that's their relationship. That whole thing must be aligned. So like if this whole thing is like 2 inches off, your core is just not gonna enter your shooter. So this is something that we didn't do because we were kind of experimenting with Master Sketch. We didn't. So since the shooter, the sketch itself was only defined to be on one perspective, so basically the side with the arm and to represent the scoring. So it didn't have this view to show the relationship between the funnel and the shooter, which is why it was kind of annoying since we have to manually figure out what's the midpoint of the shooter and then match it up with the funnel. But if this was represented in the Robot Master Sketch, to show where exactly the midline is, it's easier for the person designing the shooter at the arm and also the funnel. So that's what you should be marking in the Robot Master Sketch, the relationship in between the different mechanisms. Okay, now moving on to mechanism Master Sketch. So this is kind of similar but kind of very different. The previous one was Robot Master Sketch, so it's like a brief outline of how the robot will look like with all the key components. But the mechanism Master Sketch is specifically not for the robot, but for the mechanism itself. So like in a separate document for one specific mechanism. So it provides an additional layer of detail that you wouldn't necessarily represent in the Robot Master Sketch, and it goes into a lot more specific stuff. And it has a similar idea of having a lot of sketches in the 3-dimensional space in order to represent kind of the shape and size of the mechanism. So an example. So the example here, I think if it doesn't load, we'll just end up using the slides. It doesn't load well in school. Yeah, because we do have the photos. Actually, while it loads, let's just go. Okay, so I think what I noticed, like a lot of people on our team not knowing, is called the derive tool. So it's basically a lot of people. What I saw that we're doing is basically if you have a part and you need that part, they export it and re-import it into the document, but you have a tool called Derive, which basically lets you bring in import sketches, parts, and some features from a different document or even in the same document into another part studio or another part studio. So in this example, when you create like a mechanism, you'll be in a whole new different document other than the main robot. So like for the, let's say this is the funnel, I'll create a new document that's called the funnel, and then this will be a new part studio unrelated from the robot's master sketch. And then since I do need the important features of the robot master sketch, I'll use the derive tool to import the important parts that I need. So I don't need like let's say the elevator sketch for the funnel, or maybe I do need, but usually you don't need every single every single sketch imported into the part studio. I just basically imported all the important sketches, like the funnel sketches obviously, and I need a bit of the climb, so I just imported the things that I do really need. So on the main document, you'll make your robot master sketch, and then in your separate mechanism document, you'll bring in that robot master sketch to make your mechanism master sketch. We're closely on the tabs. Okay. Oh yeah, it did load. So basically, this is the part studio, not the assembly, and it kind of does look like the assembly, and that's like the whole purpose of it. Since you create a robot master sketch and layer it on by creating a mechanism master sketch, you'll have all the sketch related to it in its physical place that needs to be in 3-dimensional space. So if I hide all the parts, and wait, I can show, hide all the parts, hide all the planes. You see how like all the sketches form to make it look like a 3-dimensional. This is not simply just the mechanism master sketch.
This is like a plate sketch.
It's basically every single sketch that you need for the funnel, and which is also why it's kind of nice, because since you create all the parts in relation to each other for the mechanism, you know exactly where to go. So like for the entire funnel, there's basically only one entire part studio for the entire mechanism, which I thought was pretty useful. So for instance, to go into some example, I guess I'll just go into the slide. So here, basically the steps are like this. So this would be the mechanism master sketch right here. It's like very not specific. Here's some planes. And then you move on to further layer on to create the other sketches that you need. So like for all the parts. And then if you see all these new additional specific sketches create the parts for the part studio, and this is the final assembly. They almost do look nearly identical, and except the assembly just has like the duplicated parts. So yeah, that's just basically the idea of the master sketch. You create, just layer onto the robot master sketch to be more specific. So this is the next example. This is one of our summer projects this year. It was inspired after 2630. This is a double digit arm, but so I also, this is just another example to the funnel and how like things are sketched out, I guess. So let's go into the CAD. Yeah, it's probably not gonna load. Wait, actually it's probably gonna load. Yeah. So let's let it load for a while. But so the double jointed arm has two pivoting points, one here, I guess, and one down here. And in between the structures, there's like a gearbox. So all the reductions happen down here for both joints. And then there's the three motors here for both the first pivot and second pivot. Sorry. And then, so I'll show you guys how the master sketch was done for this mechanism. So first, so this is the actual order in which I created sketches. So I was thinking, what is the most important viewpoint? But then I realized I should probably start with the base because what I wanted to be parameterized was the distance between here because I wanted to try making the most compact base as possible. So I started off with the base with having variables. So we're constantly using variables as we do these sketches. So then I set the parameters for the width here. And after that, I was like, what's the next important thing? And obviously, it's the side view because it has all the pivoting points, which is what was done here. But then also what's important were the tubings for the base, which is what I added on. And if you notice that there's all the holes on the structure here because a lot of my plates and things I'm going to mount on were going to be based on these holes. So that's also what I included. So that's like the structure tubing. And then after that, the next important thing was the gearbox side view. So what I mean by gearbox side view is like where all the motors are going to be. So these represent the motors, and then where all the gears are going to be. And so all these other circles represent either the gears or the pulleys or the sprockets, like all the relationships. And if you notice, some of these are tangent because they're gears. And so all of them are in relation, like, and the reason why this is helpful is, and the reason why I made the structure first before adding the gearbox is because the shaft going through these gearboxes and the bearings that are going to be on the side should not be touching the structure, which is why it's important to have the structure tubing first before you add on the gearbox because the gearbox is related to the structure because the gearbox is not supposed to touch parts on the structure, which is why the order in which you sketch things are important. And next, we're going to go into more detail about this later, but if you see there's also a top view of the gearbox, more so because I want to know the distance in relation to like the base. Like I want the gears to be in between the base here, or like I want the motor to be mounted outside the base, and all that relationship is also important, which is why there's a top view for that. But if you notice, they're like it's all flattened down, just so because I want all the sketches to be in one and have all the relationship between each other. And then next thing, we're gonna go more into detail, but instead of the flattened view, some of these axles, I guess, such as the joints, the first joint and second joint, they have their own like axle sketch, which we're gonna go into more into detail. But it represents also the distance between each of them, because I want to know where the pulley for like the second joint is gonna go, where the tubing for the first joint is gonna go, so all that distance is like represented, and also another flat view of the second gearbox, which is just the second joint. So yeah. So now we're gonna go into axle sketch, which is basically these sketches, and also how we're supposed to make them. So the axle sketch is like the layout of the exact positions of every component along an axle. So that could be like a pivot, a roller, like a joint. And the reason why axle sketches are very helpful is because they help set the precise location of these pulleys, bearings, and gears, and all the components on that axle. And it ensures that the power transmission elements, like the pulleys and the gears and sprockets, all of them are in line with this. Because you know, when you have two sprockets, you want to make sure they're exactly centered. Also, for gears, you want them exactly centered. So the axle sketch basically does that for you. And I'll show you guys how to do it in a bit. And it also helps keep all the spacing and alignment parametric. Like if I want to shift a gear to the side, then everything along the axle, like the spaces in between, or like the distance between everything, that gets adjusted with it, so it's very parametric, which is why an axle sketch is really, really helpful. So Also, just for clarification, the axis sketch is technically part of like mechanism master sketching. It's also part of like defining the mechanism. So, anyways, what should include any component on the axle that determines like the spacing between the axles. So like, even if it may seem like so insignificant and tedious, like even the bearing flanges, like the bearing body, and like the plates, like if it's 1/8 or 1/4, and even the gears, everything important that takes up space should be on the axis sketch, except the spacers, because the spacers are just fillers to these components, the bearings, plates, and gears. So you can ignore everything except the spacers, because the spacers are just a filler. So if you have a gap between, like, let's say a gear and let's say a plate, you know there's going to be a spacer there. So you can ignore the spacer for that part. And then similar to what was mentioned before, you also want to have various planes, but most of these planes are actually from the top view. So oh yeah, I'll come back to it, but like these planes, you'll make it on this like that pivoting point and have like the plane for that. But so most of them are from like the top view, I guess. So and then the last thing you'll need, which is one of the most important things, is to link the relationship with the aligning parts. So these are like all the axle sketches. So there's like the second joint and first joint, but there's actually, so if you notice that there is a pulley, a belt going through like the first and second joint. So you obviously know that you want those two pulleys to line up exactly in the center. So that will be actually done on the axle sketch where, so I made the first joint sketch first. And then when I make the second joint, I'll look down at the first joint and I'll actually use the incident tool to physically like click the center of the pulley representing the pulley on the second joint and the first joint, and I'll like physically make it line up on sketch. So there will never be a case where it will not line up if you do this on your sketch. So this is just another example of how it relates. So this is actually the sketch for the first joint, and this is the assembly for the first joint, and this is just a side view on how the first joint looks like, which is the first pivoting part. So if you see, the sketch was done before, and then all these components were laid on top of this. So you see how like this represents the pulley. So then the pulley is here, and then this is a tubing. This tubing over here, that was also on here, so it perfectly lines up because this was made based on the sketch here. And then I also even have things like the bearing flange lined up here. Like you see the bearing flange sticking out of here. So all of that are made on the axis sketch here, like kind of like from the top view, so that like when you make these parts, they'll always perfectly line up. And you may be thinking it's kind of annoying typing out all the values for like the bearing flange thickness and like everything. You don't have to do that because most of these are parametric, so you already have a variable for that. So you have like the thickness of a gear, the thickness of a sprocket. Like you can name whatever you want, but I name my small bearing flange because the smaller bearings, and I also use bigger bearings, like the ones for the Spline XL. So you would have all these parametric variables, so you don't even have to type all these specific decimal points. If you see this in FX, here that means it's a variable. So if I know I have a pulley here, I can just like type the variable out, and so everything will be really, really fast. It doesn't take too long because you already have the parametric variables. And even the C-clip sticking out, because a C-clip's going to go on top, like a retention clip's going to go on there, you would have all of that represented. And if you notice that this part is blue, this is a personal preference. For me, I just like to save loading time, so I don't define like the length this way because I care about the length this way. But how someone else might do it, like I sometimes use the axle sketch itself to create spacers, because you could just revolve around to create the spacers, which is why for someone like me, I might actually define how like the dimensions of pulley in this dimension, how the dimensions of the pulley, this like bearings in this dimension. So it might be a personal preference, but you don't have to define everything. Yeah. Oh, yeah.
Just a question about the order that you do things in.
Mm-hmm.
So in the mechanism sketch, there's a master sketch.
Oh wait, yeah. So there's a mechanism master sketch, and there's like that's would be like all the main sketches. But wait, is your question like the difference between robot master sketch, mechanism master sketch, and axis sketch?
I get what's the order? So there's a robot master sketch, and then when you have your document for your mechanism, you derive that into your mechanism document.
Yeah.
Do you make more mechanism master sketches?
Yeah.
And then you mentioned axle sketches. So if you have two axles and a pulley between them, where are you saving the number, the distance between the axles? Is that in the mechanism master sketch or the robot master sketch?
Where
or
the
are you doing
axles?
it in the second axle sketch?
I think like you'll first have like this. You might have to it depends on which sketch you start off with. So let's say you're making a double jointed arm on your robot. You might have the side view of it in the robot master sketch because it's such an important part. Like you need the pivot points to be represented in the robot master sketch. And then in the mechanism master sketch, you'll maybe add the axle sketch. But there's usually not like a clear defined line of this up to here must be a robot master sketch and up to here must be like a mechanism master sketch. Because if you create like a sudden boundary, you get more limited. So it also depends like if you're doing FTC. So what I realized when I was doing FTC was that everything in the robot master sketch has to be a lot more specific. So I actually had the axle sketches in the robot master sketch, and so there's no like clear distinction, but it's kind of like a general idea.
So even if you make like your mechanism master sketch, you might like retrace and be like, I actually need this sketch before I made this because this sketch is linked to this sketch.
And some other mechanism lead might be like, oh, I really need this type of feature from your mechanism, so can you add that to the robot master sketch? So it's like it's not like you do this first and then you do this. You might go back and forth, and there's no really clear line between it. And then adding a limit to it might be a little more confusing. So maybe if it's easier for you, you could mix them up more, or like it kind of also depends on your preference.
Yeah, before we continue, does anyone else have questions? No? Wait, yeah?
In the robot master sketch, when you have parts that depend on coding, like if you have rollers, do you guys use exact dimensions for something like belt CBC?
Oh, for rollers? Wait, what do you mean based on pulleys? Because you could have like the distance, like the center.
Yeah, in the robot master sketch.
Oh, so I came down to this dilemma too because I don't want to draw the pulley sketch, a belt sketch on it, but I would. So if you don't have a tension or anything, I would just put the roller, because most of the rollers would have like a 1-to-1, I guess, but if you don't want different speed. So I would usually just put like a good millimeter divisible number. Like I don't draw the belt path because I want to do that on the mechanism document. I'll just make it like 500 millimeters, like a perfect distance. But I'll also decide that during prototyping because if you don't want to use a belt tensioner, so during prototyping I'll immediately decide I want to use a good divisible number by 5 millimeters, and then test that out. If that works, I'll just define that on the robot mechanism. But that's also based on preference. Sometimes I do like to draw the belts or chains or whatever. Yeah, it also kind of depends. Everything kind of very much depends. Yeah, but whatever's easier for you. So how exactly do you make okay, so how exactly do you make an axle sketch? It's just pretty short. So the first is to have a basic mechanism master sketch. So this is the basic mechanism master sketch I have for double jointed arm. So then after that you'll use the plane point tool. There's so many plane tools, but the plane point tool is really nice because first you can select. They ask you for one point and one line that you want the plane to be perpendicular to. So then you'll choose the point, which is going to be a pivoting point, like your axle, and then you'll choose any line that's perpendicular to it, so then you'll have the plane. So that's how you start off. And then after you set up your plane, then you start actually making the axle sketch. So you click on that plane, and you start dimensioning out. So I already had these bases, so then I can start adding my pulleys. I know the minimum distance I want to be, and I know where I want the bearing to be as close as possible to a structural part. So then I start defining all that. I remember the blue part I didn't define, but you guys can define if you want. What matters is the black arrow, the distance between them, that's taking up space. So, and I usually use the center point rectangle tool because I first draw a sketch for the axle itself. So then I know I know the axle is gonna stick out a little bit because the retention clip's gonna be there. And I define all that. And then I start adding the rectangle to the center point. But you see that there's an empty spot. There's empty spots here. That's because a space is gonna go there. So I don't really need to draw the spaces, just the important components. So then after that is to line things up. So what I mentioned earlier, you physically click on the incident tool, is the sketch here, this point is actually a point. It looks pretty thick, but it's actually a point. At this point, I'll actually go to this sketch because this is already defined. Now I'll click incident for these two points, and then they'll be perfectly lined up. So it will be into the tool. So yeah, so that's how the first and second joint pulley, like these here, perfectly line up, like perfectly. And if another thing that's really good, this goes for like all these like mechas and robot mass sketches, is that it's really parametric. So if I realize that I want to drag this a little to the side for some reason, then I don't even have to worry about this because this will automatically update on Sketch. Like it'll automatically update on Sketch, Parts 2, and even on Assembly. It'll just like shift together. That's really nice. So everything, so you can control everything with just one single sketch, drag it, and then everything.
Yeah, because what I notice oftentimes is people just like do the math and actually calculate the offsets in order to make it possible.
Then
And
how
that's
much-
really tedious if you have like, let's say 13 rollers on your interior.
Yeah. So like, so you don't, for this you don't have to be like, if I shift this now, do I need to take a quarter off from the spacer here to make this closer? You don't have to do all that. So it like simplifies your time a lot. And then now that I have like the sketch of where the pulley is gonna go, I actually make the pulley on the axle, so that even in the parts studio, your pulley will be located where it's supposed to be on the assembly and in real life. So you can use the derive tool. I like to use the derive tool for the pulleys too, because they let me click on where do I want the pulley to be. I can click on wherever like on the axle sketch that I want it to be, and do some like rotation, and then your pulley will be on the location where it will be. So if you see, the pulley was supposed to be between here and here because that's where our sketch is. The pulley for that is actually on there, even in the parts studio. So that's very nice. And then the next part, is even not just for the pulleys and stuff like that. You can also make like your plates. So if I knew a plate was gonna be on here, like this is a 1/4 inch plate to mount it on, I can actually make a sketch, like make a plane on that. So you see a lot of planes involved, and then make a sketch on that, and then extrude. But then the extrude is so powerful that you can click on, like if you see here, they ask you for the starting point and then like the ending point. You can click on that on the axle sketch, and then the thickness of the plate will be defined. So and let's say, oh no, 1/4 plate is too thin. I don't know why it would be too thin, but let's say I want to make it 1/2 inch. I just change that on the axle sketch to make 1/2 inch, and even your extrude will be based on that. So this one sketch can basically control everything. So yeah. And then what I mentioned before, there's another for the gearboxes. Instead of doing all these axle sketches for each like gearbox axle, I just made a flat top view because some things that are not too important and more things that you want to be in one sketch so you can easily control them around, I would usually make them in a one flat sketch. It's similar to an axle sketch that everything is just flattened down. So this is just the gearbox and motor, all the gears to get the reduction. It was like 100 to 1, 130 to 1. So all of that will be like. So if the axles aren't too important and you want multiple things to be in relation in one sketch viewpoint, you can also just do a flat top view sketch of your axles. And even the flat top view sketches, like if you have a side view and you have a flat top view, you can bring them and link them up to make a new sketch and put your gears on that. So even if you have a flat viewpoint, you can put your parts still in the location that it has to be using the other sketch viewpoint like a side view. So having a flat top view is like not that bad because you can also do this. And then you'll have something like this even with, so this is all done with the flat top view and the side view. So you'll have all your gears in relation. And for spacers and shafts, remember the empty space on the axle sketches that were supposed to be fillers for spacers? You can fill them up with the extrude. You can make a side view sketch of all your spacers, like all these black circles represent the spacers. You can then use the powerful extrude tool to click on the empty spaces that need to be filled up with spacers. And then in the end, when you do that for all spacers, you will also have all your spaces in a relative location, and they can also be adjusted based on how much you drag your sketches around. So these are just like fillers. And we also notice that we like to make these circular because they're way easier to assemble. For part studios. So for part studios, we like to keep them very, very organized. So if you see that we name all the parts, like so that anyone, like even the machinists can identify other people. We also put them in each of the folders, like electronic structure, belts, so that whenever we need to edit something, it's fine. And we also name the features. So like sometimes I usually just name the plane, extrude, and also sketch by whatever they're related to. So like like I don't have like random like plane number 3 and extra number 1, because it's really easy to tell when you derive into other documents if you have all the names like the same, so you can import them all of them together. So it's nice if you can just name all your features. Maybe not Phyllis, but like most of them. And then in the part studio, sometimes if you start doing like these efficient methods, sometimes your part studio might not load as fast, though it's worth the time because you want it's easier to make iterations. But so you have around like 50 to 60 parts on your part studio, so the generation might take long, but the feature scripts like actually have the longest time. Yeah, if you see here, you can actually see which takes the longest for your part studio to load. And since we do a thing where we do one mechanism entirely in one part studio, it does take up some time to load. So there's actually like a very good tip for it. So when I was like pocketing for the telescoping arm, I realized that these pockets, they take forever to load. So instead, I do the pockets at the very last. So I have a separate folder for all the pockets, if you see here. And there's something called rollback bar, which I realized that not many people use. It's basically just like suppressing, but like you put everything behind the rollback bar. So this acts like it never existed, and you could work on like the whole this timeline acting as if this never existed. So since this is the thing that takes the most time to load, I just act like it doesn't exist, and then bring it back when I'm done making the small edits. Then it makes your loading time a lot faster, and people always complain, oh, this takes too long to load because I have so many parts in one part studio. I think we should just make all the different parts in different part studios. So I was like, yeah, just use the rollback bar because you could just reverse the time and like hide everything that takes so much time to load. So the previous one was like short examples of like how to like for the organizing part studios and not too specific. Also, we don't have that much time. So now this is specifically for assemblies. So when I was like assembling like mechanisms on like assemblies, I was like, I have to fast and make every single thing. This is it's taking too long. It's very annoying, which is why and there's like floating fasteners, which is why I was like, oh, there's gotta be a better way to do this. And then again, this is an example. So I want to go from part studio. This is all the parts in the part studio to the assembly. And then there's a lot of like duplicate parts. There's like a lot of bolts here and there, and it takes a long time to assemble, and I don't really like that. So I was like thinking, yeah. So a tool that makes this all happen is called the group tool. I realized that it's pretty powerful, and I didn't realize this until like this summer, which I was like, and it's very useful. You can save a lot of time. So basically, what you do is you import everything. This is the part studio, so you could do insert everything from the part studio into the assembly. So now you'll have this part floating in the assembly. So what you do is use the group tool and group everything from here together. And this is possible because already in your part studio, everything is located where they need to be. In the 3-dimensional space. Yeah. So it doesn't matter if you group it because they're already in the correct location. So instead of having to fasten this plate to this pulley to this bearing, I just group everything together. Then I don't need to worry about like, oh, things misaligning and misassembling in the assemblies. So if you see here, I just group everything together in part studio. And you see here, some of them are not actually grouped together, like the motor, the sensor, the standoffs, because they're like replicates of each other. In the part studio, if you have like 5 of the same standoff, you're not going to make 5 of the same standoff. You're just going to make 1. So, and then you basically add on other stuff that are duplicates, layering onto the group. So we don't have time, so we're just gonna skip that. So yeah. So another way to keep them organized is obviously again using folders. When I went into some assemblies, there's like literally everything just floating around, all the parts like bolts and everything, which is why similar to part studios, you want them everything in folders based on the category, which makes your life a lot easier. So yeah, here are all the benefits, easier to check by mass. So like, I want to be like, oh, this whole robot weighs too much. Let me check how much all the fasteners are weighing and see if I could just replace everything to different like size bolts, let's say. So I just click on the fasteners and I could just see the entire mass of the fasteners because everything is categorized into folders. And again, like this is also very important. Use multiple assemblies. This kind of cuts your time it takes to load because it's kind of divided up into different assemblies. So this is a very, very clean example because it's an elevator. This might be a little different if you're doing like an intake or whatever different mechanism you're doing. So in the elevator, you have multiple stages: the fixed stage, first stage, second stage, and so on. So here, this is the assembly like list in the main assembly of the mechanism. There's no like lot of fasteners, nothing floating. This is the entire list. of it. There's the fixed stage versus the second stage because they're pre-assembled in separate assemblies. So for example here, on the bottom, this is the this is for the fixed stage. So on here, there's no parts from the second stage and the first stage and then reduces confusion because you only have the parts you need simply for the fixed stage. So and then if you see here, you have the fixed stage, first stage and second stage assembled separately, and then you combine them together because it's gonna go. It's an elevator. It's gonna go up and down. So you could just add the relationship between the fixed stage, first stage, and second stage, and then you could combine them all together. And this will cut down a lot of loading time. And let's say you need to edit something in the fixed stage, you just go directly to the fixed stage assembly. And you don't have to see any of these more complicated parts. And then yeah, it's like very easy to work with and it's less annoying. So how do we implement this to our team? Since a lot of these are also new, recent practices in the past 1 or 2 years. So how do we make the younger generation also continue, maybe find their own methods too, maybe use some of these methods. So first is also having I guess summer advanced CAD design lessons. So we also have CAD and design, well you see the wordplay, they're combined. But we have them for new incoming rookies too. So we continue to do that. We even did that yesterday. But how do we also get veterans, younger veterans, as they get older? How do we also make them more, I guess, used to these advanced and I guess efficient methods? So the rookies, they have their own rookie education. I guess when they come in, which is around this time before the season starts. But also during the summer, we also take that time to make sure the I guess the younger veterans to also get used to it. So we had had summer advanced CAD design lessons. You see, these are some of the examples of the lessons. We have CAD lessons and design lessons. So lots of things that we said in this presentation will also something overlap with what we talked about during these lessons. So it's every week we'll do a CAD and design lesson, and so the younger veterans can also get used to it. So. And then we also have a summer CAD and design competition. I think some people are sitting in the room right now who, this is the winner and the runner-up. You see very, very complex and well-CADed pieces. And it's what these CAD competitions do is that younger veterans can also get more practice so they can get ready for the season. They can prepare, pick up neck weights and become more experienced so they can also in turn teach the next generation of rookies coming in. So yeah, also in December you have a lot of time. They have a lot of time to experiment and work on other than school stuff. So it's a lot of fun. It's very fun to do, and everyone has a lot more time. So it's a good activity to do. But so if you see a lot of the things we talk about, they also implemented. Their master sketch looks very nice. It's similar to what we talked about. They even labeled it front. They have their field elements. They have a lot of their mechanism parts. This is the main it's the robot master sketch for them. And we also have a grading criteria that have all of these as a standard. We have sketches for the master sketch. Even the adjustability of these sketches are all the grading criteria, which is why they're able to, I guess, implement it to their work. And these are some of the other mechanisms. We have multiple groups. Even if only one group won, everyone did an amazing job with all these mechanisms: intake, double lifted arm, even end effector, even a telescoping arm. So this is the effect of the CAD design competition. So maybe you guys should also think about maybe implementing them into summer programs so that younger veterans can also get full experience. This is the contact info. If you guys have any other questions. Since we have 5 minutes left, sorry for rushing through near the end. We do want to show more examples, but there's not much time. So yeah, because this is an hour. The last 5 minutes can be used for any additional questions or anything you guys want us to go more into. Yes?
How do you number your parts?
Wait, we could just go into a document. Oh yeah. We'll show you that. While she's looking for while she's looking for the question over there, does anyone else have other questions we can answer?
Are your master sketches fully defined?
Yes.
Yes,
Mostly yes. With some
in
parts,
practice we should, but some of them, they should be.
I guess my main question is with elevators. If you have a
Oh,
shooter on an elevator,
wait.
you have that so it moves.
Oh yeah. We do actually make them move. So obviously it's kind of if everything's blue, it's kind of bad. So we just we make it like if it's cascading, we obviously just make it like look cascading in the sketches by dragging up and down. But I purposely leave it like floating in the middle and then define the length from a specific place to be like 10 inches and then just leave it there to show that the elevator can move up and down. So if you delete that, you can always just drag it up and down. But I just make sure to re-add it so not everything's not blue. And yeah, sometimes we add variables for like so sometimes we add variables. You could like temporarily add a dimension to it. So sometimes I'll do like minimum extension and the maximum of like the extension, and then I type in the extension of how much it needs to be, and then everything adjusts along with it in like the part studio. So yeah, most of them it's usually nice if everything's defined. So we usually name parts. We usually name part studios, but we don't really give number or IDs to their parts. So this is an example of the drivetrain for that.
We used to, but we realized that as long as like they have even if you don't label, as long as you have a specific name for it, machinists will be able to find it.
Yeah, so for example, here the parts, this is the main document for, let's say, for a mechanism. I usually have one main assembly, one main part studio, but obviously I need to import stuff and I need to make like small specific mounts that don't really need to be in the main one. So here are like the small part studios that I make some additional parts, but I just shove them in a folder because I don't need to access it like every day. Same applies to assemblies. There's like assemblies here. So we do a lot of organization for like the document itself, but we don't name or give IDs to specific parts. So if you see here, they're all named by like front guts or whatever. They're named by what makes sense.
But we used to give part numbers, but we realized it wasn't that.
Yeah. So, but the document itself, they all have good IDs.
Yeah. Oh, so every week this could be on through Zoom. This was done through Zoom actually, but we have one design lesson. So we'll go into like compression, how to calculate torque, how to use like the calculator to get what ratio of gear reduction you need, and if that's like the design. And then we have like a CAD lesson where we go more in depth on how to do these things we mentioned in the presentation. So like the axle sketch, that part was also like part of the lesson where so the kids will know that, which is why each of the tools are mentioned, because I also brought this from the summer CAD design lesson, so to give step by step on how to do it. So that's kind of like how it's structured.
Yeah, and then they have a project to combine both their design knowledge and CAD knowledge to do them together.
So it's like design lesson, one CAD lesson, and then like a project.
Yeah. And then every week they add on to their project based on with the new stuff they do.
Any other questions? Yeah?
Calculate like gear ratios with something like recalc?
Yeah. It seems to work out pretty well.
Yeah,
for us.
Yeah.
Any other questions before we're ending soon? Yeah.
Would you have any suggestions for how to pocket things, or like just a general sense of how to pocket things efficiently?
Yes. We did. Yeah.
There's actually like two ways we do it. One is like just use the feature script lighten for it's like very popular. It's like right over here where wait, there's
okay, and so first, yeah, lighten is the most popular tool. It's kind of nice. You just draw lines. Yeah, and the second method is kind of uncommon, but sometimes manual pocketing is really useful. So what I realized was when I was like designing like the telescoping arm, it basically has like a pocketing with law of triangles that are just basically uniform. And sometimes when the pocketing location of the pocket really matters. So for instance, in the telescoping arm, the bearings in the interstage. So the bearings in the interstage must slide not on the pocket, so the location of the pocket really matters. Sometimes you want to manually pocket.
But most of the time we'll make like these lines that goes to where like the force is like will be concentrated, like
the drivetrain, the wheels will be spinning. That's where there'll be a lot of force. So we draw.
So we map it out, and then we use the lighten tool. Like you guys can just search up. It's called
It's a feature script.
Yeah, it's a feature script, and we just click on these parts and then automatically.
Yeah.
Okay.
But sometimes manual pocket. Sometimes manual pocket is useful.
Okay. Well, that's it. Thank you guys so much for coming.